Hello students, today's video is concerned to Vant Hoff factor and abnormal molecular weight. I am Dr. Prashanjit Mukherjee. Welcome to my channel. Well, the Vant Hoff factor, if you want to define, the Vant Hoff factor is usually represented by the letter I, and it is actually a concerned relationship that is being identified on the basis of the experimental and the theoretical colligative properties, to be precise, and is defined as the number of moles of particles formed in the solution per mole of solute. It is a property of the solute and it does not depend upon the concentration of the ideal solution. Okay, but remember, however, the Vant Hoff factor of the real solution may be always lower than that of the experimental values. So this has to be represented, and therefore the Vant Hoff factor for non-electrolytes, the strong electrolytes, and all the factors are being expressed over here with a mathematical derivations. So I will explain it one by one, and the notes has been shared in the description box. Now we are just explaining the whole of Vant Hoff factors on the aspect of colligative properties. Just now I have told you that colligative property theoretical is not equal to colligative property experimental. Now what does it mean? As you know, that colligative property is dependent upon the number of particles over here and does not depend upon the nature. And you have to know that the components of the colligative properties as vapor pressure, osmotic pressure, elevation in boiling point, depression in freezing point. Okay, so what happens? This is what you see: vapor pressure experimental by vapor pressure theoretical is equal to molecular weight theoretical by molecular weight experimental. Why is that so? The reason behind is that if I take into consideration about the molecular weight, and PV is equal to nRT is known about it, that means PV will be equal to what? W by M into RT. Therefore pressure is inversely proportional to molecular weight is coming up. So that's why you find it out osmotic pressure experimental will be molecular weight theoretical, that's inversely proportional to each other. So osmotic pressure experimental by osmotic pressure theoretical. Okay, and that is equal to elevation in boiling point experimental by elevation in boiling point theoretical is equal to depression in freezing point depression in freezing point experimental by depression in freezing point theoretical, and that is equal to total number of moles after dissociation by total number of moles before dissociation. And that resembles to that of what I, that is called Vant Hoff factor. Now students, just see over here, if you want to find out a Vant Hoff factor representing the whole of electrolytes, that is a strong electrolyte, I have mentioned all the things in the notes over here, and if you want to find out for the strong electrolytes and the degree of dissociation is, say for example 70% of say CaSO4. So here it is what CaSO4 can be segregated into dissociated into the formation of Ca++ and SO4 minus minus, So here it is coming out to be what? Number of particles becomes 1 and 1. That is total number of particles as 2. So you just apply this particular functions of Vant Hoff factor. That is what? 1 plus n minus 1 into alpha. What is alpha? N is what? Number of particles, and alpha is the degree of dissociation. So 1 plus 2 minus 1, there are 2 particles, into alpha is how much over here? 70%. So you will find it out that what? 1 plus, it's coming out to 1 into 70% is there, that is 0.7. So that is equal to 1.7 is the value for a strong electrolyte. For a non-electrolyte, so the Vant Hoff factor will be always equal to, say, C6H12O6. You cannot dissociate. That means number of particles remains 1, and that is why the Vant Hoff factor will remain to be as 1. But for dimerized compound, for association group, association is what? You will say, for example, CH3CO, which is the, say, 20% of associated acetic acid. So CH3CO, which is the 2 molecules, the association because of dimerization, and this becomes CH3COOH whole twice. And this is what? 1, 0 initial concentration, and this 1, 0 at equilibrium concentration. Is 1 minus alpha dash alpha, or you can write 1 minus alpha dash by 2, and this is what? Alpha. Okay, instead of writing this one 2 alpha and all. Okay, so you can write this one as like this way. This is becoming what? And coming up to be, sorry, it's a mistake over here. This becomes 1 minus alpha, and this is alpha dash alpha by 2. So this is total number of moles after association becomes 1 minus alpha plus alpha by 2. That is equal to 1 minus alpha by 2. Just now I have told you that is coming up to be, so this is 1 minus alpha by 2, this will be, this is just now I have told you that this Vant Hoff factor is always represented as total number of moles after association. Okay, and total number of moles before association. There is another one we can do, dissociation or association. Okay, or association. So it can be a dissociation or it can be an association. There is total number of moles after this dissociation or association, or total number of moles before dissociation or association. So total number of moles after association is coming up to 1 minus alpha by 2, and this is divided by 1, that is equal to Vant Hoff factor, and it's 20%. That means this is coming out to 1 minus 20 by 2, okay, into 100. Okay, so this is coming out to be I functions, and that will come, whatever the values is there, you can get it to be done. 10 times goes, this is 1 by 10, that is equal to 1 minus 0.10. Okay, so this is coming out to be what? That is 0.9 is coming, so that is that is coming out to be 0.9, and this is less than 1. So we can just take into consideration that if it is dissociation, the trick is what? Dissociation, the I value will be always greater than 1. If association, the I value will be always equal to less than 1, and if it is non-electrolyte, I value will be 1. Now students, the molecular weight, abnormal molecular weight, we are finding out the abnormal molecular weight due to degree of dissociation. Okay, so what's the option over here? AB is there and can be dissociated in the formation of A plus plus B minus over here, and we can take it as initial concentration in mole, that is equal to 1 and 0 and 0, and then at equilibrium concentration in mole, and that is really concerned to 1 minus alpha and alpha, where alpha is degree of dissociation, remember. So this is total number of moles after dissociation, number of moles after dissociation becomes 1 minus alpha plus alpha plus alpha. This is cancelled out. This is coming out to 1 plus alpha. So here we know that Vant Hoff factor can be resultant functions of molecular weight theoretical by molecular weight experimental. Just now we have discussed is equal to total number of moles after dissociation. Total number of moles after dissociation by total number of moles after total number of moles before dissociation. Okay, so this is coming out to be mth by m experimental will be equal to 1 plus alpha by 1. So you can cross multiply this one. This will becomes m experimental plus alpha into m experimental is equal to mth, and that will be considered to be as what? Alpha will be equal to mth minus m experimental by m experimental. This is degree of dissociation, abnormal molecular weight due to degree of dissociation. Similarly, abnormal molecular weight due to degree of association. Due to degree of association. That is equal to CH3COOH, and this is two molecules. This is dimerized compound, and this becomes CH3COOH twice. This is 1 0 1 minus alpha and alpha by 2. Okay, so this is total number of moles after association. This becomes how much over here? This becomes 1 minus alpha plus alpha by 2. This becomes 1 minus alpha by 2, and that's why molecular weight theoretical by molecular weight experimental. Here alpha, you can just mark it as differences, alpha dash, so that it can be easily differentiated between degree of dissociation and degree of association. So molecular weight theoretical by molecular weight experimental is equal to total number of moles after association by total number of moles before association. Okay, so the whole thing can be written to be as mth by m experimental will be equal to 1 minus alpha by 2 by 1 alpha dash by 2. So you can easily find out the value of alpha dash from here. Okay, so this is coming up to be what? Mth. This is coming up to be m experimental, coming up to be mth is equal to 2m experimental minus m experimental into alpha dash by 2, and that's 2mth is equal to 2m experimental minus m experimental alpha dash, and that's coming out to be m experimental into alpha dash will be equal to 2 m experimental minus m theoretical, and alpha dash will be equal to 2 m experimental minus m theoretical by m experimental. This is how we find out the degree of association. Students, thank you for watching this video. Share at most to your friends and make this channel a bit popular. Thank you.